Okay, so now at this point, what I want to do is a couple of, really one application problem, which will be after this example, but I also want to do an example that mimics what we saw a little bit of in 4.1. So just as a reminder, all throughout this section as well as 4.1, we've been finding these antiderivatives, and in that process, you get this constant of integration, that plus c. And remember that plus c represents some arbitrary constant. However, if we are given additional information about our function, which comes in this form, I call this an initial condition, then we can use that initial condition or that extra information to determine what c is equal to in this particular case. So I want to do that here. There's nothing new about this concept. The only thing that's new is that in order to find the antiderivative we're looking for, we need to use u substitution. But aside from that, it's the same type of problem that we've already encountered. So if we're asked here to find f of x given that f prime of x is equal to 4x to the fourth times the cube root of 2x to the fifth plus 64. In addition to that, we have this initial condition, f of 0 is equal to negative 36. Let's begin by setting up an integral, because if I integrate f prime, it will give me f of x plus c. So the integral of f prime, I'm looking at 4x to the fourth times the cube root, and I already know that it's going to be more helpful to write this as something to the 1/3 power, so I'm just going to do that here. 2x to the fifth plus 64. It's cube root, so that's to the 1/3 power dx. Okay, it's this integral that I want to solve. And as we have seen, when you have something that appears in a set of parentheses like this, most of the time that is going to be your best choice of u. So I'm going to set u equal to 2x to the fifth plus 64. The entire function in that set of parentheses. This would mean that du is equal to 10x to the fourth dx. Looking at what we actually have outside of our parentheses, it's pretty close to what we see here. We have the x to the fourth, but where I have a 4 in my integrand, I have a 10 over here. So once again, as we've seen multiple times now, we want to force a 4 to appear here, and I can get that by multiplying both sides by 4/10. 4/10 du equals 4x to the fourth dx. Again, I do that because I want to multiply by a fraction whose denominator matches this constant, causing it to cancel out, and whose numerator is whatever number I want to replace that by, 4. This is fine, but the 4/10 here can be simplified. Let's write it as 2/5. 2/5 du equals 4x to the fourth dx. Okay. So now I can start making some substitutions. Going up here to my original integrand, the 4x to the fourth and the dx here together, when those are multiplied, that forms 2/5 du. So I can write this 2/5 outside of my integrand, or integral, and then the du I'm going to save that for the end. So looking at what's left, I have this stuff in parentheses, all of which I'm calling u to the 1/3 power. This whole thing reduces down to u to the 1/3 power times du. Okay, now that's an easy integral to do. So all I need to do there is, I have my 2/5 here still. I add 1 to the exponent, right, which is 4/3. Then I multiply by the reciprocal of that, which is 3/4. Okay, I get a little cancellation happening here. That would give me 3/10. So this is equal to 3/10 times u, but let's replace the u with this guy here. U is 2x to the fifth plus 64 to the 4/3 power plus c. Okay, so at this point it feels like we're done, because in all of the examples we've looked at up until this point, this is where we would have stopped, except we have this initial condition. And this initial condition is going to give us a means for finding this number c right here. So how do we find that value c? Well, I plug 0 in for x, and I set it equal to negative 36. So negative 36 is equal to 3/10 times. Now, if I plug a 0 into this, this first term just goes to 0, and I'm left with 64 to the 4/3 power plus c. Now let's think about what that would be equal to. So 64 to the 4/3 power. The denominator of that rational exponent tells me to take a cube root, and the cube root of 64 is just 4. Then I raise that 4 to the 4th power, and 4 to the 4th power is 256. And so what this tells me is that negative 36 is equal to 3/10 times 256 plus c. And from here, there's a little bit of arithmetic to do, and I'm not going to do it all for you. Basically, you would need to multiply this fraction by 256. There's a little cancellation. These are both divisible by 2 right here, for example, and then subtract that over here to get c by itself. I'm going to let you work out the arithmetic there, but I can tell you what c is going to come out to. It comes out to negative 564 over 5. Okay, now that's not my answer. That is what I have to put into this c here to get my answer. So now I know this. F of x is equal to 3/10 times 2x to the 5th plus 64, all to the 4/3 power, plus c will actually look like minus 564/5. Okay? So again, in this problem, it looked very similar to all the other examples we've already done, but we had one additional step where we had to determine what c was equal to given this additional information up here. Okay, we have one last example to look through. This one is a word problem, and it's going to be similar to stuff we've done before, but again, the only difference is that we're going to have to use the use substitution technique as a part of solving this problem. So here's the explanation. Dice Dice Baby, which I think is an amazing name for a company, has found that its marginal profit function for making and selling polyhedral dice sets is given by this function. P prime of x is equal to 6x over the square root of 7x squared plus $20 per dice set when x dice sets are made and sold. If the company's profit from making and selling 500 dice sets is $240, what is the company's profit from making and selling 600 dice sets? So to solve this problem, it's a lot of the same stuff that we have been doing, but I want to point something out. Notice right here where it says the company's profit from making and selling 500 dice sets is $240. A profit function is where we would get this information from. So our first goal is actually to determine what our profit function is, P of x. I don't know what P of x is, but I do know what P of 500 is. It says when I sell 500 dice, I get a profit of $240. Okay, this is like that initial condition that we saw up here. So I'm going to use that to solve for that constant of integration c once I've gotten myself to that step. But if it's just P of x that I want, I know that at least P of x plus c, well, let's just call it P of x for now, I can find by taking an antiderivative of P prime of x, which is 6x over the square root of 7x squared plus 20 dx. Okay, so here is where I'm going to need to use the use substitution. I need to take the integral of this, and within this function, I see a composite function. I see a square root function with another function sitting inside of it, 7x squared plus 20. Because that is inside the radical, that is my clue that I should be setting u equal to that thing. U is equal to 7x squared plus 20. Okay? So from here, let's see. My du, what would du be in this case? 14x dx. Okay? Compare that to what we actually have in our numerator, 6x dx. So almost the same, but the constant is where we differ. And again, that's not an issue. Multiply both sides by a fraction whose denominator is 14 to cancel this 14, and whose numerator is 6, the thing I want to replace that by. So that would be 6/14. 6/14 du is equal to 6x dx. And then let's simplify that fraction. I could divide by 2 to give me 3/7. Du is equal to 6x dx. Okay, so let's rewrite our integral now in terms of this u. My integral is going to have this 3/7, which I'm going to pull out like we've been doing. And then I have a du here, together with that 3/7, over the square root of just u. I'm going to write that as 1 over the square root of u, du, like this, which we know is better if we write it this way, u to the negative 1/2 power, du, like that. At this step, I want to take the antiderivative, so I add 1 to my exponent, which would give me a positive 1/2. This is going to give me u to the positive 1/2, and then I multiply by the reciprocal of 1/2. The reciprocal of 1/2 is just 2, and if I multiply the 3/7 that's sitting out here by 2, it becomes 6/7. Then I have that plus c there. Finally, replace the u by the function we defined it to be equal to. So that would be 6/7 times the square root of 7x squared plus 20. And then I have this plus c, right? And as before, that plus c is the thing that I want to solve for, because if I can solve for that, then I have my exact profit function. I have p of x. In fact, what I could do is over here, I could say p of x is equal to this, right? So let's use the initial condition. I want to plug 500 into this function, and then I want to set that equal to 240. So 240 is equal to 6/7 times the square root of 7 times 500 squared plus 20 plus c. Okay, I seem to have lost the part of my notes where I solve for c here, so I'm going to try and do this manually. Let's see how far we get. So this means that 240 is equal to 6/7 times the square root. Now 500 squared, 5 squared is 25, and then I'm going to have 4 zeros after that. So that'd be 250,000. 250,000 times 7 is equal to, what is that equal to? That would be 1,750,000 plus 20. I'm going to have 6/7 times 1,750,000 20, but not 200. Okay, let's do this. This is one reason why it's a good idea to use pencil instead of pen. 240 equals 6/7 times the square root of, we said 1,750,000 20 plus c. Okay, so here's what I'm going to say, because I have an answer for this problem, but I'm missing my value of c. You are not actually obligated to get c in an exact form. We can leave it in radical form. So let's do this. This may be unsatisfying, but I can write c as 240 minus all of this stuff, 6/7 times the square root of 1,750,020. Okay, this I can now plug in for the c up here. So I have p of x is equal to 6/7 times the square root of 7x squared plus 20 plus this constant, so plus 240 minus 6/7 times the square root of 1,750,020. Okay, this was not really what we were asked for. It didn't just say find a profit function. Specifically, it said find the profit from making and selling 600 dice sets. So what that is P of 600. So we would go in here, we would plug 600 in. 6/7 times the square root of 7 times 600 squared plus 20 plus 240 minus 6/7 times the square root of 1,750,020. That all goes into a calculator. Don't try and do that by hand. You're going to get a nasty decimal, but remember, we're talking about dollars and cents here, so it makes the most sense, no pun intended, to round to the nearest cent. So I'm going to say that this is $466.78. I do have the answer, I just didn't have the work leading up to that. So this is how we would solve a problem like this. And once again, notice we were given a marginal profit function, which again is always defined to be the derivative of a profit function. And then from that, I used an integral to find the profit function. I took an antiderivative, but that profit function, because I found it using an antiderivative, had a plus c in there. That function is not very useful unless you know what that c is equal to. We used the additional information, again, which I'm calling an initial condition, in this problem to plug stuff in and solve for that c. We rewrote our profit function with that known value of c, and then we plugged in the number that we cared about to get our actual profit for that. Okay, that is the end of 4.2.